This is Math 432, Applied Combinatorics. I am Professor Asaph, and today we're going to be paving the roads. Consider this town. What we want to do is think about how bad it would be if the roads weren't paved. So think about each of these as a dirt path from one house to another. And when it rains, they're pretty much impassable. The bus just can't get there. This boy on the bike will definitely go skidding. Okay, so what we want to do is we want to pave the roads, but we want to do it in the most cost-effective way possible. So, for example, if we pave this road and this road, there's really no need to pave that road too, because, well, you can just go the long way around. It's not a problem. So the mayor of the town decides, okay, I'm going to pave the roads in the most efficient way possible. So what are we trying to do? What's the idea here? The solution to this problem is a very common problem in graph theory, which is to find a minimum weight spanning tree. So we've talked about graphs and we've talked about trees, and now what is a spanning tree? So given a graph G, given G, any graph, a spanning tree for G is a tree T on the same vertex set. So if we have a graph, then if it's connected, we can always find a spanning tree. Think about why that is. What property of a tree will let you know that you can always do that? Of course, if the graph's not connected, you're not going to be able to find a tree. But what we want to do is we want to turn this into a graph theory problem. I mean, it kind of looks like one. All the houses seem to be the vertices, and the roads, of course, are the edges. So let's go ahead and make our graph. So this is a graph rendition of the same town. So you can see that I can line up my vertices. So these three here or these three here, and then this little house is this one. So I've got all my edges in here. But there was another constraint that we said, which is minimum weight. So the weight is important, the cost for each road. So let's assume that the number of flagstones connecting each path tells me the weight. So here there are 2 flagstones. That'll say this weight of this edge is 2. Here, there are 3 flagstones. So this guy has weight 3. I can count up here at the top. There seem to be 5. So we'll put the 5 down here. And I can just go ahead and fill out the weights on all of these different paths around the town. So we could have a very complicated network like this. And in fact, this is a network problem when you're putting phone lines or putting cell towers, things like this. We often have minimum weight spanning tree problems. And the graphs get big and cumbersome and complex. I think I've forgotten this one. Okay, so now we have all our weights in here. So how are we going to find a spanning tree? So what's a spanning tree? So it's going to be something like maybe this. Hold on. Have I got them all? No, I need one more. Here. This is an example of a spanning tree. It's a tree. There are no cycles you can check. And I've touched every vertex. Okay? So it's connected, touches every vertex. But I don't know if that necessarily is minimum weight. The weight is going to be the sum of the weights along the edges of whatever path I take. So what I want is some algorithm, some procedure that can tell me definitively how I should do this. So the algorithm that we're going to look at is called Kruskal's algorithm. And it's an example of a greedy algorithm. So a greedy algorithm is just sort of at every step you do the best thing for that step. You look locally instead of looking globally. Greedy algorithms are usually fairly easy to implement, but they don't always work as well as you think. So how are we going to start? We're going to start with F. So F is going to be the edges that we're considering. So this is going to have no edges. We're going to populate edges into the set F. And we're going to do it according to the following rules. So once we have F initiated, so F initially is the empty set, what are we going to do? We're going to consider all edges of the graph that are not yet in F. Okay? We're going to delete any that create a cycle. And then among the rest, choose a minimum weight edge to add to F. And then when do we stop? Stop when F is connected. So when the edges I get are connected. So I can think about that in my graph here, and let's say we're going to highlight, let's pave the roads. I realize that it would probably make more sense to pave them in a nice gray color, but let's make it show up. So we're going to pave the roads in red. Okay, so what does Kruskal's algorithm say? It says, okay, look at all the edges in my graph that are not yet in F. Well, F so far doesn't have any edges, so maybe I'll remind you here that F is going to be the highlighted edges. Highlighted edges. Okay, so let's go. So what's the minimum weight I see? The minimum weight is 2. So I see 3 different edges that I could take. Oh, 4. 4 different edges that are minimum weight. And I can just take whichever one I want. So I'm going to take this one. Oh, let's take it with a highlighter so it shows up a little better. That's the edge I'm going to take. Great. Now that was doing the first step. So now iterate. Go again. So that's got me one edge. My graph's not connected. The graph with just these highlighted edges is not connected. So I look again and I say, okay, well, I want to take all minimum weight edges. So where are my minimum weight edges? Well, here's a minimum weight edge. I could take this one. Didn't create a cycle, so I'm allowed to do it. Okay, look again. Minimum weight edges. This one doesn't create a cycle. This one doesn't create a cycle. Great. So I've taken all my smallest weight edges. That's fantastic. Now keep going. I don't see any more 2s, so I'm looking really among the 3s. So I'm going to take this edge here. And now we have something interesting. Now I'm looking at the edges again, and I look at all the edges, and remember, I'm going to want to take the minimum weight, which right now is 3. So I've got this candidate, this candidate, this candidate, this guy, and this guy, except I can't take this one. Because if I took it, then I would have a cycle. So that guy is out. And in fact, it'll never be back in. So I'm going to go ahead and cross it out. Once it's eliminated in this case, it'll never be included again because we've already said it's going to create a cycle. So, okay, maybe I'll take this edge. Okay, and now look again at all of my edges. Are there any that I can't take that are weight 3? No, they all seem good to me, so I'm going to take this one. And now look again, what can I take? Well, I think I'll take this one. Notice I'm making a choice, and if you made a different choice, you would get a different answer. And that's important to keep in mind. Now we're back in the case where I need to rule out this edge because that would create a cycle. But that's okay. I've still got a weight 3 edge I can take. So there's a weight 3 edge. And now I'm done. If you notice, I've now covered every vertex. So I wasn't paying attention to that. I wasn't paying attention to the fact that I would cover every vertex. But now I've done it. Now I've got a tree. And so now we are done. And now we can ask ourselves, what's the weight of F? It's going to be the sum of the weights of my edges. So I see that from the top, I've got a 3 plus 3 plus 2 plus 3 plus 3 plus 2 plus 2 plus 3. So this is how I would determine the weight of the graph. Now notice, even without computing the weights of all possible spanning trees, I can see that I never took a weight that was bigger than 3, right? None of these numbers is bigger than 3. I took every single one of the 2s. I didn't skip a single 2. So this has to be a minimum weight spanning tree. There's no other option. So in this particular case, Kruskal's algorithm worked. It gave me a minimum weight spanning tree. We're going to consider these intermediate steps that we got where we got a forest. A forest is just a union of trees. We'll consider some properties of those next, and then we'll use those properties to prove that Kruskal's algorithm always gives us a minimum weight spanning tree.